Double integrals in polar coordinates, starting with number 15 by popular demand. Evaluate the given integral by changing to polar coordinates. So double integral over R of arctan of y over x dA, where R is the region in the xy plane such that x squared plus y squared is between or greater than or equal to and less than or equal to 4, and then y is less than or equal to x greater than or equal to 0. So first things first, they don't say to do it, but what must we do? Not yet. Draw the region, graph the region, right? Okay. Here's how you have to think about it too. When you're changing from rectangular to polar, I was thinking about it last night, because you know how the classwork yesterday, you guys were just plugging in how the formulas are equated, like from rectangular to polar, and you can't change the limits that way, because you're not going from one rectangular system to another rectangular system. The way polar is defined is totally different. So it's not as simple as just like replacing all of the equations. That's why you have to graph it in order to see how do I describe this rectangular coordinate system region with polar coordinates. It's not as simple as just swapping the equations out. You know, you do that for the integrand, but not to determine the limits of integration or how the region's defined. Okay, so x squared plus y squared between 1 and 4, what is that going to look like?
2 circles.
Yeah, and the radii are 1 and 2.
1 and 2 circles.
Yeah, please be sorry. No, it's okay. So here, let's say this is 1, and then copy, paste, let me stretch it. Does that look like it's about double?
Yeah.
I think so, huh? Okay, 1, 2. So we have the region between these two circles and including the boundary of the circle. And then here, think about it this way. This is the line y equals x. But y has to be less than or equal to x, so that's going to be the region below that line, but above the x-axis, because it's also greater than or equal to 0. So the line y equals x, do you know what angle it makes with the positive x-axis? Pi over 4. Oh my god, you guys know so much. Okay. Pi over 4. But we have to have only this portion here, right? So can you identify what's the region R that they're describing? What's the intersection of those two inequalities going to be? It's just going to be right in here, this little piece. Should I shade it in more? Yeah.
1, 2.
Between 1 and 2. Yeah. So theta is going to be bounded between.
0, 5.
Beautiful. And then R. 1 to 2. Good. And if you want to do the same little, remember I told you draw a ray outward. Where it hits first is the lower limit, 1. Where it hits second is the upper limit. Okay, good. That's all I'm doing today. Okay. Now, from here, I think we're ready to go. So we're going to have integral 0 to pi over 4 on the outside, then 1 to 2, then arctan, switch this to polar. Y is r sine theta. X is, beautiful, and what's dA?
R, dr, theta.
Good. Okay. And then look what happens. R's cancel. We have sine over cosine, which is tan. Arctan of tan theta would give us back just theta. Perfect. So this is theta. 1 to 2. 0 to pi over 4. R dr d theta. Okay? Can you just slap a pi over 4 on the outside?
Yes.
No, because there's a theta. But you can split this up into two integrals because all of the limits are constant. Okay? So what you could do is go 0 to pi over 4, theta d theta, that times integral from 1 to 2 r dr. Okay? If there was no theta, though, yeah, you could just put pi over 4 outside and get rid of the d theta. But I think you guys have it from here, yeah?
Yes.
Okay, so this is going to be 1/2 theta squared from 0 to pi over 4. And then this is 1/2 r squared, but be careful, from 1 to 2. So what is this? Pi squared over 32, yes, thank you. And then the other one's going to be 4 over 2, so 2, minus, oh, so 3/2, yes? So then this gives me 3 pi squared over 64. You guys seem like you were not stuck. You just wanted to watch me do it?
I feel like the setting it up the arc 10 and 10. Yeah.
Oh, it made you nervous? Do you want me to write more steps?
What I did, because like I couldn't do it, the answer was like 10, so I was like, I did a triangle instead.
You did a triangle here.
It was like y over x is like.
Okay. This is arctan of tan theta, right? So as long as this is within the domain of arctan, what's the domain of arctan? Domain, not, you're telling me the range. What's the domain? All real numbers, right? Domain is all real numbers. So you can plug in any real number here. Arctan of tan theta, that's going to be well defined. That's fine. So that just gives us back theta. Good? Okay. Yeah, then it was like not a crazy integral at all, right? Yeah. Okay. You want to set up 17, right? Whew. Okay. Use a double integral. So we have to be obedient. You guys know Calc 1 style because it says use a double integral to find the area of D. So what would the setup look like if we're doing a double integral to find area instead of volume?
It's just dy dx.
Well, put dA, because most likely we're going to go polar. Also, too, I don't like to write dy dx until I decided that's the order of integration I want to do. Because what if you want to do dx dy instead? So when you're not sure, like when you haven't committed yet to the setup, just put dA.
Okay.
And then we'll integrate over the region D. Double integral over D. This gives you not just A, let's be specific. This is area of D. So you can use that notation, area of the region D. Okay? Now let me draw it here. They gave it to you because this one was kind of spicy. But I think you probably could have graphed it, right? It just might have made you nervous. So it's 2 cardioids. And they told us this one is r equals 1 minus cosine theta. And then here, this is r equals 1 plus cosine theta. And then the region D, okay, pretend those are the same, right? So I drew it a little deformed, but it's okay. That's D. All of it. So what I'm going to do is actually just find the area of the top half and then I'll double it. Okay. And just using the graph, you should be good to go. So the area is going to be 2 times. Now look here. This area right in quadrant 1 is determined by which polar curve? 1 minus cosine theta. All of this. Can you see that? So if you go from theta equals 0 up until the area is determined by, and you could even draw the rays if you want, right? It goes from 0 to 1 minus cosine theta. So theta is going to go from 0 to pi over 2. R would go from 0 to, very good. That's for that first portion. Portion 1. Portion 1. Now the part in quadrant 2, okay, theta is going to go from, no, it'll start here. Yes, pi over 2 to pi. And then R is determined by, it starts at 0.
So 1 plus cosine.
1 plus cosine theta. Very good. So you don't have to actually like find the intersection or do one minus the other or anything like that. If you look at it, all of that area in quadrant 1 is determined by 1 minus cosine theta, and then all of the area in quadrant 2 is 1 plus cosine theta. You could keep going for quadrants 3 and 4, but by symmetry, let me just do these two integrals and then double it and be done with it. Okay? So then, do you want me to set it up or you got it from here?
You set it up.
Yes, I'll set it up with pleasure. Okay, so area is going to be 2 times, we'll have integral 0 to pi over 2, 0 to 1 minus cosine theta, and what's dA in polar coordinates? Perfect. Plus, the other integral, theta is going to go from? Good. And R?
0 to 1 plus cosine theta.
Good. And dA is?
R theta.
Good. Good. If you added a function here, now what would this represent? A volume, exactly. Yeah, of something, whatever you've decided to put as the integrand, okay? So I think some of you guys were making that mistake too yesterday on the last classwork problem, number 8. Some of you were putting something to integrate. And it's like, if they ask you for area with a double integral, you have nothing besides dA, no function, okay?
So area is just the two bounds which represent two dimensions.
Yes. Remember what I showed you guys that when we first started talking about multiple integrals, every integral sign is like a dimension. So that's why like this gives it, when you were in Calc 1, this is area, because here's 1 dimension, 2 dimensions. If you have a double integral and no function, then it's also area, it's 2 dimension. If you have a double integral and a function, now how many dimensions? 3, so that's a volume. And then today we're going to do triple integrals over E with a dV, no function. What would that be? Volume, there you go, you got it. Now, are we going to do triple integrals with a function, dV? Yeah. What does it mean? I told you guys, if F is like a density function, then that would give you the mass of the solid. If it doesn't have a specific interpretation like that, then it's some 4-dimensional quantity. We don't really describe with the application, okay? And then we'll do in chapter 16 integrals where instead of F of function, you have a vector valued function. So that's the craziest it's going to get. But it's fun. Yes, it is nice. Okay, you feel good with 17?
Yes.
Yes? Oh, I'm so happy. Okay, 21. Was it just hard to draw the rows?
Yes.
Yeah. And just remembering like values associated with it, so like to know that it's pi over 3.
Okay, I'll show you like a good shortcut that I always show in Calc 2, because I don't want you making a table if you don't need to. Do you know what I mean?
Yeah.
So 21, again, use a double integral to find the area of D, which is one loop. And it tells you which one. Loop of the rows R equals sine 3 theta in the first quadrant. Okay. So when the coefficient on theta is an odd number, that's how many loops or petals there are on the rows. So we're going to have 3 of them. So you can draw the whole thing if you want. This one, I'm trying to think, is it like this, this, and this? Yeah, okay. So anyways, that's sloppy. We're going to just put together one loop here. But I want to motivate like the trick I'm going to show you. Okay, it's not really a trick, but okay. To figure out how long it takes to trace out a loop, you want to set the rows equation equal to 0. Because R starts at 0 when you start tracing out a loop, and then once it makes its way back to 0, then one loop, one petal has been traced out. So what I want to do is solve basically sine 3 theta equals 0. For all real valued solutions. So think to yourself, when does sine equal 0? 0 plus pi k, right? Where k is an integer. Right? 0, pi, 2, pi, infinitely many places, yes? Okay. Now to isolate theta, I would divide through by 3. So theta equals, we don't need the 0, right? Forget him. Pi over 3k, and there we go. So every pi over 3, a loop or a petal is traced out. That should tell you pretty much your limits of integration. The only one that's funky is if it's cosine instead of sine, it looks like this instead, the first one. So in this case, we're going to go 0 to pi over 3. But sometimes you have to go, if it was cosine 3 theta instead of sine 3 theta, you would go negative pi over 6 to pi. Okay, but anyways, I'm getting ahead of myself. So don't always assume you're going to start at 0. In this case, we are, though. So every pi over 3, a petal is traced out. And then just plug in something for theta to see where you're starting. So I would just plug in 0 to start. And then I would see, okay, r of 0 would be sine of 3 times 0. So that's 0. And then I know the next time it's going to be 0 is add pi over 3. So at pi over 3. And then it's sine of 3 times pi over 3. So that's 0 again. When does the petal reach its max length? Halfway between. So that would be at pi over 6. So that's sine of 3 times pi over 6. Sine of, pi over 2. No, am I forgetting the 3 in the front? No. Yeah, it's just sine 3 theta. Okay. So then it's just going to be 1. Okay. So then you get as carried away as you want. Like here's the 45-degree line. So whatever. I hate that. Hold on. Pi over 360. Let me put it like here. And then halfway. It's not my drawing day. Okay, good? And that's all we need. You don't need the full rows because they only wanted one loop anyways. So let's set it up. Area. Theta's going to go from?
0 to pi.
Good. What about r?
0 to the front.
Yeah, 0 to sine 3 theta. If you get nervous, start at the origin, draw ray outward. Start at the origin, draw ray outward.
Does it not technically also touch 1? Like 0 to 1? Or...
But it's not always 1. It's always ending at sine 3 theta. It's only 1 specifically at pi over 6, right? If it was always 1, it would be a... Yes. Yes. The radius is constant on a circle. This one is not. Okay? So shall we set it up? 0 to pi over 3. 0 to sine 3 theta. What's dA? Good. Do you need help integrating? No? You're good?
I have a question.
Yeah.
So, my point of confusion is when we have a theta equals pi over 3k,
Mm-hmm.
and you say we know our limit bound of integration, what you're saying is that because we know that that first petal will always happen every pi over third,
Yeah.
we can just say that we don't need to calculate infinite petals since it's always the same area, which is why we can
Yeah,
say,
and they wanted the one in the first quadrant.
which is why we can just say from 0 to pi over 3, that dimension.
Someone riding a bicycle in the hallway?
It's just gas.
Oh.
Yeah. Well,
Oh.
so that's why we can say from 0 to pi over 3 for theta, that gives us the domain of that single petal. by
Yeah.
itself.
Let me change it.
Okay. And why did we do R0, R pi 3, R pi 6?
Just so we get the lengths so you could
Oh,
see.
so you can accurately, like,
Because
draw
what
it.
if it was r equals cosine 3 theta? I want you to see the difference in the setup. So you would start the same way. You would say, okay, cosine 3 theta is 0. So when is cosine 0? Pi over 2 plus pi k. K is an integer. So then now theta equals
Pi over 6 plus pi k.
pi over 3k.
Pi over 3?
Yeah.
Oh,
You have to divide everybody by 3. Okay, so then the difference is, if you sit there and try to trace it out,
Symmetrical with the x-axis.
Yeah, so it starts, so say this is your pi over 6 line. It would start here. If you kept adding, you're going to get a different petal. Oh no, why did I draw it all the way up there? That's when it's 0. Whoopsie daisy. Okay. So if theta is pi over 6, here, let me plug it in. R of pi over 6 is cosine 3 times pi over 6. That's 0, right? It's not going to come out nice. You don't get the petal that's right here if you keep adding to this. Yeah. So what comes out nicer is if you do 0 next, because then it's cosine of 0, which is 1. And then r of negative pi over 6 is when you get back to 0. So you actually have it live like in here.
So plugging in your R values for petals is both to help you draw it accurately and be able to see what's happening.
What the limits of integration should be, yeah. And then like this one, I would, if you want to set it up in the beginning and go negative pi over 6 to pi over 6, 0 to cosine 3 theta. And then in the next step, I would just double it and then go 0 to pi over 6, right?
So this is pretty like intuition, isn't like you need to just remember your critical points for the petals?
Yeah, or just understand the idea, because when there's a different number of petals, it might look different, right? Because if you change the 3 to a 5, then you'll have 5 petals, so it'll be oriented differently. So don't memorize. I'm just saying, understand that if it's sine versus cosine, they lay differently. And then depending on the coefficient, you have a different number of petals, so they're arranged differently. But if you just remember, always set r equal to 0 and solve, you'll know at least how long it takes to trace out a petal, and then you can plug in whatever values to figure out which petal you need.
So always set R equal to 0, that'll show you where the petals are balanced, and then plug in some values for R or something.
Yeah, so you can draw a petal.
Okay.
Good?
Yeah.
We can practice a rose today. The rose made you nervous?
It's just
Oh
been
no,
so
it's
long.
been so long.
So
I mean, yeah,
I don't think I've seen
last time I did this was in like
You
high
didn't,
school. High school.
Calc 2, you were supposed to do polar at the end.
We didn't do it.
We did it for like a day, and then we didn't do it on the exam.
This is BC Calc.
Yeah,
Wow.
yeah, that was the last time.
What happens? Did you learn it in BC?
Yeah, it was on the test.
Your teacher did a shoddy job.
Yeah.
Seth over here knows it all. And he learned trig sub in 5 minutes. That wasn't, you didn't know trig sub from the AP test, I heard.
No. Well, I did for the AP test, and then I forgot it.
You forgot it? Oh no. Okay, that was 21. Let's do 35. Use polar coordinates. Now we're finding volume of the solid that's above the cone, z equals rad x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals 1. Okay, let me write this down. So the solid is above the cone. They're so nice, they told you it's a cone. Appreciate it. And then below the sphere, x squared plus y squared plus z squared equals 1. So we're going to have to draw a 3D graph of the solid as well as 2D graph of the base region. To figure out what the base region is in the xy plane that we're going to be integrating over, we need to find the intersection. I think the easiest thing to do is square both sides here. So z squared equals x squared plus y squared, and then substitute that into the sphere's equation. Did you guys start that way? Okay. So intersection x squared plus y squared plus another x squared plus y squared is 1. So then you get x squared plus y squared equals 1/2. So what's the radius? 1 over root 2. Good. And then they're basically going to intersect if x squared plus y squared is 1/2 when z equals square root of 1/2. So also at 1 over rad 2. Yes? And notice we're using just the upper half of the cone because we only have the positive radical. So We're only going to be interested in the upper half of the sphere as well. Let's graph everything out right now. So 3D graph required. 2D graph also required. Here's Z, here's X. Okay. So the sphere has radius 1. Is that clear? The sphere, radius 1. So here's the sphere. And then the cone is opening upward. Okay. And then they're going to intersect in a circle when Z is equal to?
1/2.
Very good. And then this is the base region that we're going to integrate over. Imagine it like projected down in the XY plane. That's what we're going to integrate over. Okay? So what's that region look like? We just solve for it here. It's a circle. And radius is 1/rad2. Scoot, scoot. Okay. Let me shade it the same. Okay, perfect. Now, let's identify the solid because we're going to have to do top minus bottom. We're actually integrating a function now because we need a volume. So the solid is above the cone and below the sphere. Yes. What does it look like though? Shade in the region. It looks like ice cream cone. Yes. Does it look better upside down?
I mean,
Can you see it? Like an ice cream cone, snow cone?
Yeah.
oh, snow cone.
Snow cone, that did it? Okay. You don't eat like the drumstick ice cream cones ever? Yeah. Yes, Roy.
So the radius of the circle and height of it from the origin is both 1/rad2.
Yes. The base region?
Yeah.
Yeah.
Well, let's be like that. Or-
No. This was special. Yes. Okay. So let's set up our limits of integration. Theta will go from 0 to 2 pi. We're going all the way around. All the way around. Okay. And then R is going to go from 0 to 1/rad2. And then you're going to have for the height, top minus bottom function, right? For the height of your solid. So if you need to, let me switch colors though. Draw a ray going in the Z direction. Where it hits first on the solid is bottom. Where it hits second is the top function, right? So which one's on the top?
Yes, spheres.
The sphere. So now we need to solve for Z though. So Z squared equals, come down here, 1 minus x squared minus y squared. Z equals plus or minus square root. Let me get the ball rolling, switch that to r squared because I know we're working with polar coordinates. Now do I choose the positive or negative radical? Positive, good, because it's the upper half of the sphere, right? So top function is going to be rad 1 minus r squared minus what's on the bottom,
Rad r squared.
which is just r. Perfect, the cone. Yes. Good? Okay, so then now we're ready to put it all together. So you're going to have integral 0 to 2 pi, 0 to 1/rad2, rad 1 minus r squared minus r times r dr d theta. Ooh, can we take a shortcut? You can just put a 2 pi outside, right? And then go 0 to 1/rad2, r times the square root of 1 minus r squared dr. Now, what would you need to do for this first term to find the antiderivative? U sub, but we're going to do it in our head very savagely. Are you ready? Yes, not savagely, elegantly, like we're in a math competition. Because once you get used to it, it's going to be, you can write out the first line if you need to. We would let u be, so du would be, well, I have RDR, so I'm just going to pick up a -1/2, yes? Okay, so here we go. You're going to have 2 pi, we're picking up a -1/2. I'm going to have 1 minus r squared raised to what power now? 3/2, because it's currently raised to the 1/2. I'm going to add 1 to the exponent. We divide by the new exponent, so what should go out front? 2/3. There you go. Then I didn't have to split it into 2 integrals. I didn't have to do the u sub and change the limits of integration on one of them. You know what I mean? It's just so clean. And then when you get used to it, you might not even need to write that much out for the u sub. You'll do it in your head. Minus, what's next?
R cubed over 2.
Good. 1/3 r cubed. I mean, you could write r cubed over 3. I just hate it. So sorry, I won't. I won't do it. And then 1 over rad 2. Are you good from there? Yeah? Okay. And then you should get pi over 3 times 2 minus rad 2. Yay! Beautiful. That was 39?
30.
Oh, 35. So I got one more. 39. Oh, love it. It was kind of like what you did yesterday for classwork. Who needed 39? Mustafa, it's you?
I thought, because like, my question is, why did I not go from 0 to 2 pi? Sorry, from 0 to pi. I went from 0 to pi over 2.
Did you graph the integration region?
Yeah.
Okay, you see how x goes from 0 to 2?
Yeah.
So that means already you're only either in quadrants 1 and 4, because this is x equals 0, the y-axis. The y-axis is x equals 0. This is half a circle, really, right?
Was it the top half? It's 4 minus.
Yeah. So it's the 0 to rad 4 minus x squared would be top half. Yeah. But then x is also only from 0 to 2. So this is x equals 0. This is x equals 2. So it's only this part.
Oh.
If it was going to be all the way from 0 to pi, this should have been -2 to 2. Then it would have ended up 0 to pi. This is 0 to pi over 2.
It's like the most out bound of integration always gives you the like how far you are.
You have to describe a quarter of a circle. So you need to figure out from these limits of integration, it's only 1/4 of the circle, not half. You should be able to tell just by these limits. If these are the bounds for y, we're going from x-axis up to the top of the circle. And then the bounds for x tell me we're only in quadrant 1.
From this side.
Yeah, 0 to 2. So that's how you know, oh, it's only 1/4 of the circle, not half the circle. Yeah. So you have to carefully, that's why I would draw it. I would draw it. Do you need me to do the integral or you're okay from there?
I found it.
It's a relaxing u sub.
Yeah.
Okay. Good. Was that all right? You seem fine. Okay, then let's do triple integrals, right? Let's spice it up. Oh, it's going to be fun, Vincent. Don't worry. Okay, that's it. Don't forget to give the video a thumbs up, like and subscribe. I'll link the video lecture for this section in the description. Follow me on Instagram and TikTok, Math with Professor V. Say bye, you guys.
Bye.